Welcome to today's paper reading. Today's paper is titled Sora, a review on background, technology, limitations, and opportunities of large vision models. This paper was published on the AR14 preprint by Yixin Liu and colleagues from Lehigh University and Microsoft Research. The Sora model, released by OpenAI in February 2024, is a groundbreaking text-to-video generative AI. It is designed to create videos of both realistic and imaginative scenes from text instructions, showcasing its potential in simulating the physical world. This paper provides a comprehensive review of Sora's background, the technologies that enable it, its applications across various industries, and the challenges it faces. Key areas of discussion include ensuring safe and unbiased video generation, and exploring how future advancements could enhance human-AI interaction, thereby boosting the productivity and creativity of video generation. Figure 1 highlights Sora, a significant advancement in AI-powered vision generation. This model, released by OpenAI, excels in creating high-quality, up to 1-minute-long videos from text prompts, ensuring they closely follow the user's instructions. This capability marks a leap forward in AI's ability to understand and simulate the physical world dynamically and contextually. The introduction of ChatGPT in 2022 marked a significant transformation in AI technologies, leading to the release of OpenAI's Sora in 2024. Sora is a text-to-video generative AI model capable of producing high-quality, minute-long videos from text prompts. Unlike previous models, Sora maintains high visual quality and adheres to complex user instructions. At its core, Sora uses a pre-trained diffusion transformer and space-time latent patches to efficiently generate videos through an iterative denoising process. Figure 2 showcases examples of Sora's text-to-video generation capabilities. The OpenAI Sora model is given text instructions, and it generates 3 videos based on these instructions. Sora is capable of producing detailed scenes that include multiple characters performing specific actions against intricate backgrounds. One of the most striking aspects of Sora is its capacity for up to a minute-long video, while maintaining high visual quality and compelling visual coherency. This capability represents a leap forward in AI-driven creative tools, allowing users to convert text narratives to rich visual stories. In the field of computer vision, traditional methods such as texture synthesis and texture mapping were based on handcrafted features, but they struggled with complex image generation. The advent of generative adversarial networks, GNs, and variational autoencoders, VEs, revolutionized image generation, followed by advancements like diffusion models. Recently, models like Sora have demonstrated emergent abilities, including the generation of videos from text instructions, showcasing significant progress in the field. Figure 3 illustrates the historical progression of generative AI within the vision domain. It highlights the pivotal roles of generative adversarial networks, GNs, and variational autoencoders, VEs, in advancing various applications. The integration of the transformer architecture from NLP into computer vision tasks, such as Vision Transformer, VIT, and Swin Transformer, further propelled the field. Additionally, diffusion models have significantly enhanced image generation capabilities, providing a mathematically sound framework for converting noise into detailed images. Sora is a diffusion transformer with the unique capability of flexible sampling dimensions. Its architecture is divided into 3 main parts: a time-space compressor, a vision transformer, VIT, and a clip-like conditioning mechanism. The time-space compressor maps original videos into latent space, the VIT processes tokenized latent representations, and the clip-like mechanism conditions the model with LLM-augmented user instructions. Sora's data pre-processing involves training on videos and images at their native sizes, transforming diverse visual inputs into a unified representation, and employing a video compression network built on VAE or VQVAE. In terms of modeling, Sora utilizes various diffusion transformer variants, video diffusion transformers, and focuses on enhancing instruction following capabilities through detailed captioning and prompt engineering. Figure 4 provides an overview of the Sora framework, detailing its 3 main components. Firstly, a time-space compressor transforms the original video into a compact latent space. Secondly, a vision transformer, VIT, processes this tokenized latent representation to output a denoised version. Lastly, a clip-like conditioning mechanism uses augmented user instructions from a large language model, LLM, to guide the diffusion model in generating styled or themed videos. This reverse engineering of Sora's technology highlights its innovative approach to video generation. Figure 5 illustrates the capability of Sora to generate images in a variety of sizes and resolutions, from 1920x 1080p widescreen to 1080x 1920p vertical formats. This flexibility allows Sora to maintain the original aspect ratios of the input data, which empirical findings suggest leads to more natural and coherent visual narratives in the generated images. This approach contrasts with traditional methods that often resize or crop images to fit a uniform standard, potentially losing important visual details and consistency. Figure 7 illustrates Sora's method of transforming videos into patches. Initially, videos are compressed into a lower dimensional latent space, which is then decomposed into space-time patches. This process is crucial for the unified visual representation required for large-scale training of generative models. The compression network used is based on VE or Vector Quantized VE, VQVE, as referenced in Sora's Technical Report 3. Figure 8 illustrates the process by which VIT, Vision Transformer, handles image data. The image is first divided into fixed-size patches. Each patch is then linearly embedded, and position embeddings are added to these embedded patches. This sequence of vectors is subsequently fed into a standard transformer encoder for further processing. Figure 9 compares different methods of patchification for video compression. On the left, spatial patchification samples NT frames and embeds each 2D frame independently following VIT. On the right, spatial temporal patchification extracts and linearly embeds non-overlapping or overlapping tubelets that span the spatio-temporal input volume. This comparison highlights the differences in how each method handles the spatial and temporal dimensions of video data. Figure 10 illustrates how patch packing allows for variable resolution images or videos while maintaining their aspect ratio. This technique treats token dropping as a form of data augmentation, enhancing the flexibility and efficiency of processing diverse inputs. The method is sourced from NavIT 40, highlighting its application in preserving the integrity of visual data during compression and transformation. Figure 11 presents the overall frameworks of DIT and UVID. DIT employs a multi-head self-attention layer and adaptive layer norm, ADLN, with an additional MLP layer for zero initializing, which stabilizes the training process. UVID treats all inputs, including time, condition, and noisy image patches, as tokens and proposes long skip connections between shallow and deep transformer layers, achieving record-breaking FID scores in image and text-to-image generation. Both models demonstrate scalability and flexibility, replacing the traditional UNet architecture in diffusion models. Figure 12 illustrates the comprehensive framework of the Masked Diffusion Transformer, MDT. The figure clearly differentiates between the training and inference processes for each time step using solid and dotted lines, respectively. Notably, masking and the side interpolator are integral components during the training phase but are excluded during inference, highlighting the dynamic adaptability of the MDT framework. Figure 13 illustrates the overall framework of Imagen Video, a text-to-video generation system developed by Google Research. The system employs a cascade of 7 submodels that handle text-conditional video generation, spatial super-resolution, and temporal super-resolution. A frozen T5 text encoder generates contextual embeddings from the input text prompt, which are injected into all models in the cascade. The base model generates low-resolution videos, which are then refined by cascaded diffusion models to increase resolution. The architecture uses a 3D UNet with spatial-temporal separable layers to capture interframe dependencies. It employs V-prediction parameterization and conditioning augmentation for stability and parallel training. Joint training on images and videos, treating each image as a frame, leverages larger datasets. Classifier-free guidance enhances prompt fidelity, and progressive distillation streamlines the sampling process, reducing computational load while maintaining perceptual quality. This combination allows Imagen Video to generate high-fidelity and controllable videos, capable of producing diverse content in various artistic styles. Figure 14 illustrates the framework of Video Latent Diffusion Model, Video LDM. The process begins with the generation of latent keyframes, which are then subjected to 2 rounds of latent frame interpolation to achieve a high frame rate. Finally, the latent video is decoded into pixel space, with an optional video upsampler applied for enhanced spatial resolution. This approach allows for the generation of globally coherent long videos in a computationally efficient manner. Figure 15 illustrates a case study on prompt engineering for text-to-video generation, using color coding to outline the creative process. The text highlighted in blue describes the elements generated by Sora, such as the depiction of a stylish woman. Conversely, the text in yellow emphasizes the model's interpretation of actions, settings, and character appearances. This demonstrates how a carefully crafted prompt is transformed into a vivid and dynamic video narrative. Figure 16 demonstrates how image prompts are used to guide Sora's text-to-video model in generating dynamic content. The red boxes in the figure highlight the key elements of each scene, such as monsters with varied designs, a cloud formation spelling out Sora, and surfers navigating a tidal wave inside an ornate hall. These visual anchors ensure that the generated video aligns with the intended narrative and visual themes. Figure 17 showcases the video prompt techniques used with Sora models. In Part A, the video extension technique involves the model extrapolating the video sequence backward from the original footage. Part B demonstrates video editing, where specific elements such as the setting are transformed according to the text prompt. Lastly, Part C illustrates video connection, where 2 distinct video prompts are seamlessly blended to create a coherent narrative. Each process is guided by a visual anchor, marked by a red box, ensuring continuity and precision in the generated video content. The advent of advanced video generation technologies is revolutionizing various sectors. In film production, these technologies enable the autonomous generation of movies from simple text inputs, significantly reducing costs and enhancing creativity through AI. In education, dynamic video content tailored to individual learning styles enhances engagement and understanding. The gaming industry benefits from real-time video generation, creating immersive and responsive game environments that evolve with player actions. Figure 18 showcases the diverse applications of Sora across various fields. In the movie industry, Sora enables the generation of film-style videos from detailed scripts, revolutionizing movie production. In education, it transforms static resources into dynamic, engaging video content, enhancing learner engagement. Within gaming, Sora's capabilities in generating high-fidelity video content and realistic sound effects promise more immersive and responsive game environments. These applications highlight Sora's transformative potential in content creation and problem-solving across different domains. Sora demonstrates notable capabilities in video creation, particularly its ability to produce 1-minute videos with consistent and engaging storytelling. It excels in handling complex interactions, marking a significant improvement over previous models. However, Sora faces limitations in physical realism, where it struggles with accurate depiction of cause and effect. It also has issues with spatial and temporal complexities, such as confusing directions and maintaining temporal accuracy. Additionally, Sora's human-computer interaction is not fully developed, making detailed modifications challenging. Despite these limitations, Sora presents significant opportunities. In academia, it encourages exploration of text-to-video models. In industry, it has potential for enhancing realism in game development and advertising. Socially, it can democratize high-quality video production, benefiting content creators and journalists alike. In this conclusion, the authors present a comprehensive review of Sora, which is based on a survey of published technical reports and reverse engineering from existing literature. They plan to continue updating the paper as more information becomes available, particularly when Sora's API is released and further details about Sora are revealed. The authors hope that this review will serve as a valuable resource for the open source research community and lay the groundwork for the community to develop an open source version of Sora. They invite discussions, suggestions, and collaborations to achieve this goal. Thank you for watching.